Hello, everyone. Thank you so much for joining us today. My name is Ashley Skitt, and I'm the Marketing Director here at Tempo Communications. Welcome to our webinar, Troubleshooting Two Wire Systems with a Milliamp Clamp Meter. We're just a couple minutes away from some awesome content. You will all be on mute throughout this webinar, but we do encourage you to use the chat function or raise your hand. And if you have any questions during the presentation, we're happy to answer those. There will be time at the end as well for questions and answers. This webinar is being recorded, so you will receive a link after the webinar in about 5 business days to the recorded version of the webinar. It will also be posted on our website under education and on our YouTube channel. So you can see all our past webinars there as well. Today, your presenter is Alejandro Aste-Nieto. He is the Associate Product Manager of Irrigation here at Tempo Communications. Alejandro strives to gather voice of customer insights for irrigation's electrical troubleshooting tools. Drawing from his experience in tech support, he possesses an understanding of irrigation system faults, tool tester functionality, and troubleshooting methodologies. He is committed to continuous learning, having attended various trainings from experts in the fields of irrigation, and is also an expert in the field of irrigation himself now. Without further ado, I'll turn this over to Hondo.
Thanks a lot, Ashley. Thanks everybody for being here. We're going to talk about two-wire troubleshooting with a Milliamp Clamp Meter. Two-wire is a very quickly growing technology in irrigation and something that I think people are still getting used to and understanding how to troubleshoot. And Milliamp Clamp Meter is a very powerful tool when it comes to troubleshooting for a few reasons that we'll get into. So we will be just doing an overview on two-wire systems and their components, talk about where there are weak points in that system to look for problems. We'll talk about the Milliamp Clamp Meter itself, and then how to troubleshoot with it, some of the concepts, some of the measurements we're going to be taking, some strategies when you're trying to narrow things down, and then some example problems. So let's get right into it. What is two-wire? Well, it's two-wire for a reason. Only two wires are needed to operate many valves out in the field. So we have a controller, and we just have two wires coming out of the controller that can operate lots of these valves out there, as opposed to the typical system you'll see, or the more conventional system that has been around for longer, where there's a valve going, a wire going to each valve. So in this kind of system, a decoder is required to operate a valve. So it's kind of acting as a middleman between the controller and the valve itself. So in a two-wire system, the two wires should always be kept separate, not touching where they shouldn't be touching. They're always going to be, they should always be separate colors, so you can help keep track of the two of them and keep things separate, keep things aligned, and to know if there's a problem on just one wire, you can make sure that you pay attention to that wire further out in the field. And in many two-wire systems, there's communication happening between the controller and the decoder. There's some diagnostics that a decoder will do out in the field and communicate that back to the controller. So for that to happen, there has to always be electricity on this two-wire path carrying voltage at all times. Not all systems are like that, but many of them are. They take advantage of having a decoder out there and communicating back and forth. So some of the components that we can break down here. So like I said, there's a controller at the very beginning, obviously, and then the two-wire path connects out to a valve box somewhere. This diagram is obviously like a very simplified version of what's happening out in the field. So valve boxes will all be connected along a two-wire path. It's important that there is grounding every so often, because since this is all just one big linked system, it could all be damaged with just one bolt of lightning. So grounding is important for damage protection. And with each grounding plate or grounding rod, there will need to be a surge arrestor to help redirect voltage away from the valuable components. And then inside a valve box, we have the valve itself. We have the solenoid that the wire, the wiring comes down and operates with electricity to open the valve. We have the decoder there in the middle, and connecting the decoder and the solenoid are the two splices connecting the two valve wires to the decoder. These are direct bury waterproof splices, and then we also have another two direct bury waterproof splices from the decoder to the 2-wire path. So each and every valve box has a minimum of 4 splices inside it, a lot more than you'll see in the conventional system where controllers are wired directly to solenoids. So, and at times have a decoder operating more than one valve. In this situation, we have one decoder with the ability to talk to 2 different valves and operate them individually. And then just to talk about what is a decoder, really, it's, again, the middleman between the controller and its signals and the valves themselves. These are using power and digital communication from the controller to direct valves appropriately. They are uniquely numbered, waterproof, and programmable, and they can operate multiple valves, up to 6 as far as I'm aware. I haven't heard of anything higher than that. So the path, you'll have voltage and digital communication going out along the entire path, and they'll reach each and every decoder. However, the decoders are only going to operate if they receive specific instructions per their unique serial number coming from the controller. So in this example, to operate this first valve, there is voltage and instructions coming from the controller, and it's reaching every single decoder, but this is the only one who says, oh, this is my name being called, and I'm going to operate my valve here and water my zone. So, again, some systems, they only have voltage when there's a zone being operated, and there's no two-way communication happening when the system's idle. And therefore, there's nothing for your clamp meter to measure, by the way. We'll talk about kind of how to handle that, but just understand that for some situations, some systems, there's no current flowing when the system is idle. For other systems, there is. So just to compare the wiring coming from a conventional controller and a 2-wire one. So as you can see here, in a conventional system, tons of wires coming from the controller, one for every single valve out in the field. So the more valves out there, obviously, the more wire. If you compare that with a 2-wire system, a lot less wire is required, especially when there's a lot of valves. You can operate hundreds of valves from one controller in a 2-wire system, and they can all use the same wire path. Usually you'll want to kind of break things up into multiple wire paths, but you can connect a lot of valves just on one wire path. And yeah, obviously the main benefit is less wire use, but these systems are also much easier to expand, because if you wanted to add a zone, let's say out here, rather than running a wire all the way from that zone to the controller and adding one more wire into your big bundle there, all you have to do is stick another 2 wires onto the end of this 2-wire path, and you've now linked it electronically. You obviously still have to put your water pipe there as well, but you don't have to dig up anything past the furthest valve to be able to expand. And these systems can operate valves from very far away. So some of them, valves three miles away, give or take. And again, dozens of valves along that same wire path out to that very, very far valve. These systems tend to start to make more financial sense when we have a lot more valves to operate, because you're saving that much on wire. But on smaller systems, it doesn't always make financial sense, because decoders are not negligibly costly. They tend to be at least retail for $100 each or so. So right when you get to maybe 30 or 40 valves or more, it starts to break even and then be cheaper when you're using less wiring on a 2-wire system. Obviously, there's other benefits in terms of just the simplicity and the ability to do diagnostics and easier to install with less wires going in, but those are the main benefits. So the different 2-wire systems can look a little different here. In these maps above, we have little line segments that are just connecting between valve boxes. They're just little runs of 2-wire cable, solid 2-wire cable runs. The dots are these valve boxes. The rectangles, they're the junctions where the path might branch off into different directions to connect to other valves out there. And these entire sections that stem from the controller are what you would call a wire path. So even though there's multiple branches here, these are all one wire path. And so ideally, this is all one color of cable, and then this is a different color of cable here to kind of help you understand where you are and keep things separate. But it's not always easy to do that in practice. And then we can configure these in this branched star pattern like this. Certain systems, when you loop things, the loop can start at a controller and then end all the way back in the same controller in a different port. Some systems, they don't allow that. You can still do loops, but those loops can't come all the way back to the controller. They might have to end early. And there's pros and cons to doing loops. I think it adds some redundancy, whereas, if you have a break, say here, this valve is still connected because it's still got a path back to the controller. And you can get to further distances with loop patterns because there is basically voltage support coming from both directions. But these systems are harder to troubleshoot, so it's recommended to break loops when you're doing troubleshooting, and we'll talk about how to do that. And obviously, it's very important to understand where everything is in your system. And if you don't have a map already, you're going to need a locator to help you to find things. So when it comes to locating, make sure that you have your black lead going to a ground stake and your red lead clipped to both wires in the 2-wire cable. You do not want to connect each lead to each wire. That can introduce decoder damaging voltage across these 2 wires, whereas this, you'll at least have the same signal being applied to both wires, same voltage, and the decoder will not feel the difference in a sense. This also will give you the best signal because now there's signal coming on, the same signal on both wires here, and it basically just gives you twice as good of a signal. So when it comes to locating, just remember this is the correct way to do it. You can connect to just one wire, but you might as well just connect to both. There's just a little bit less risk of damaging things, and it's a better signal. So where to look for damage? The leading causes of failure are going to be primarily a bad splice. Could also be a failed decoder, or the itself could be damaged. But the vast majority of problems, including failed decoders, are caused by compromised splices or potentially damaged wire insulation due to stripping the jacket to prepare for a splice. You could, when you're removing the outer jacket to expose the inner 2 wires, you have to be careful not to damage the inner conductors, and it's very easy to do. So it's just another place where water can introduce itself. And typically a decoder will fail because water is allowed in to the conductors and can be attracted into the electronics of the decoder. Especially these systems that have 2-way communication, there's constant voltage and current going on, that literally attracts water into these exposed crevices. And when you have electricity combined with water, it dramatically accelerates corrosion. So These systems where there's constant communication happening, they are much more susceptible to failure from poor splices. So talking about splices, this is an entire topic unto itself, but we'll just kind of touch on it a little bit. A good splice, the wires are undamaged. It's important not to over tighten the twist on these wires. When you're stripping the inner wires in the cable, you have to be careful not to nick the copper in there, because obviously when you do that and then you twist, and then the system operates a valve and then shuts off, and then there's electricity coming and going, things are heating up and cooling down. Those stresses can over time cause problems. So these systems are very sensitive to good splices. And then obviously you want the wire nut to be pushed all the way to the end of the tube here to give you a protective layer of waterproof gel from here all the way to here, and give you lots of protection. This wire nut that's not pushed into the tube is offering little to no protection. All the sealant is up here at the end of the tube, not blocking water from getting in to your connection right there. Gel-filled wire nuts are not enough protection for these 2-wire systems, especially the ones that are doing the two-way communication and have the constant voltage going on. There are certain systems where, like Hunter has the easy decoder system that only operates or only has voltage when a zone is operating, and they say you can be a little bit more flexible with your splices, and they say you can get away with these. So take that with a grain of salt, but in general, splices are very important when it comes to 2-wire systems. Obviously, these are just not going to hold up whatsoever. Again, I'm tempted to delve further into talking about how important splices are, but we're here to just kind of talk about the clamp meter and how to troubleshoot with it. But let me just mention that there are entire schools of thought about how to do good splices. The person I've talked to with the most experience and best track record that I know of is Noe Cruz. He has a very helpful video on YouTube talking about his own method that he claims has 100% success rate. So I recommend you look that up. His channel's, I think it's under his name, NOE, first name, last name Cruz. Noe Cruz, he has I think it's like a 20-minute video talking about his method, which isn't necessarily the industry standard method of doing things. So check that one out. So now talking about the clamp meter, the CMA 360B. So the reason why a clamp meter is such a valuable tool is because you can troubleshoot these systems without breaking connections using a clamp meter. You can troubleshoot 2-wire systems without a clamp meter, but that involves taking the wire path apart and breaking it in half and seeing if your problems go away, and then reattaching and then breaking another section, and sometimes taking measurements of resistance or voltage along the way. But obviously, when you're breaking connections, not only do you have to get a little bit more dirty, but you have to replace these connections, and those are not free. You have to spend the money on more splices. And then you might be breaking good connections and then introducing new problems on the second time around when you have to resplice. So a clamp meter is just, if you're doing any 2-wire troubleshooting, it's going to pay for itself very quickly in time and materials. So the way it works is you measure the outgoing current on the 2-wire path, and then you can sense what's happening downstream. So good decoders, depending on the manufacturer and type, they typically use somewhere in the range of 0.5 milliamp to 5 milliamps when they're idle. When they're operating a zone, they'll use more, but it's best to kind of do your measurements when a system is idle, and kind of look for these consistent numbers. If you have obviously a system will all be using the same manufacturer of decoder, as they are not compatible from one to the other. But even, one manufacturer will have one system that needs one kind of decoder and another system that uses another kind. So decoders are going to be very consistent in your system, and they will use a consistent amount of current each. And we can use that to our advantage when we're taking measurements and doing some math. We can also take some other measurements with the leads here with voltage and resistance, which is very helpful. So ideally, your clamp meter measures below 1 milliamp, because as you can see here, we're dealing with things that measure in fractions of milliamps. Ideally, it has true RMS for the most accurate readings, especially if you're taking measurements while the system is idle and operating normally. Some systems might use a 60 clamp meter friendly 60 hertz. Other ones use a very unfriendly wave. And then ideally, your clamp meter also has the ability to take these other measurements as well. So just to revisit the concept of Ohm's law with current, voltage, and resistance, keep in mind that voltage is like electrical pressure. So if you think of this water system with a pump, the pump is what's providing the voltage or the pressure. The electrical current, which is what we're measuring with the clamp meter most of the time, is like the flow rate of electricity, and it's a lot easier to think of in terms of water, right? So it's with more pressure here, the more quickly water will flow, and then the resistance is the restriction on that flow. So again, the more pressure and less restriction there is, the more flow. So the amount of current that we measure tells us a lot about what's going on out there. And coming back to the topic of the wave current waveform. So typical AC that you get when you plug into a wall, at least here in the United States, is 60 hertz. I know we're talking to some people out there in Australia where it's 50 hertz, but it's always going to be a smooth kind of back and forth wave, either 50 or 60 hertz depending on where you are. Some systems operate off of 24 volts of AC at either 60 or 50 hertz. And that's very friendly for clamp meters. Other systems will use very odd waves that might be very slow, like one time per second. It'll switch kind of back and forth between positive and negative voltage between the two wires. So, for instance, the Hunter ICD system will be 1.2 hertz of a very square alternating current wave, so a very different wave than what's typical out there. And then the good thing is true RMS, which is built into the CMA 360B, will make good sense of waveforms that are not very smooth like this. Most meters out there just sort of assume this is the shape of the wave, and they kind of do rough math to give you a current number, but this actually calculates for any kind of waveform. So that's helpful for two-wire, obviously. When there's two-way digital communication, there's very rapid bursts happening on the two-wire path. So as you can see here in this image, there might be the slow pulsing happening, but then all of a sudden there's very rapid bursts adding to the amount of current going on. But we can sort of help to ignore some of those bursts kind of messing with our readings by engaging a low pass filter. And the low pass filter of the CMA 360B starts to kind of ignore anything above 160 hertz, and the higher the frequency, the more it'll ignore it. So helpful to know on those kinds of systems. So when we begin our troubleshooting process, obviously we want to start at the controller, and it can tell us a lot of information. For one thing, is it able to turn on? If not, let's just check for anything obvious. So power switch, did that somehow get flipped? Did a fuse blow? Is the supply voltage correct? Is the transformer working correctly? Is the voltage coming out of there within our range? If all that checks out, let's see what's going on that in the wire path that might be introducing some problems. Let's remove our wire paths and then switch the controller back on. If it's still not working and there's nothing connected to the controller, there's something happening in the controller that we need to know more about. There might be some LEDs to help us there. Otherwise, you might need to contact the manufacturer and just see if they have any other tips. Otherwise, that controller might be damaged and might need some repair. However, if we remove some wire paths and the controller now turns on for the first time, that indicates there was an overcurrent that the controller refused to operate with in order to protect itself. So that means we probably want to take some measurements with our clamp meter. And in order to do that, we need a source of power. So if the controller refuses to turn on and give us that power, ideally it will have a short finding mode or a wire test mode like some of the newer and more sophisticated systems have. Otherwise, if the controller can't really help us, we can build our own power supply, and we'll talk about that. So if the controller is turning on, we want to just kind of see what new information it's giving us now. Is there an overcurrent error? Is it just sort of forced into that short finding mode and telling us, yes, there's a short out there, there's an overcurrent happening? If so, we want to break any loops that there might be in the system. So if we have this looped system here and we break the connections at the far ends of all these loops, we basically turned it into a star pattern system with branches. So we'll be able to think of everything in that system in terms of upstream and downstream now, which is helpful when taking clamp meter measurements. Here, if you're here and you're measuring what's upstream and what's downstream, because you're in a loop, you're in a circle. So we want to be able to break the furthest points in a loop if we're troubleshooting that system. So once we've done that, we're going to want to disconnect the two wire paths, the two wire cables, one by one from the controller, and see if that changes anything. See if our controller says, oh, the problem has gone away. So once we do that, we can verify that the cable path is the one to introduce that problem. We can try to reconnect the cable and see if it all of a sudden starts working and that was just a fluke and there's no problems now. Or if you can reconnect the cable and the error returns or the shutdown happens again, you verify that there is currently a problem on that wire path. And then that typically will mean that there's an overcurrent, there's a short out there. And that's something that we can find with our clamp meter. And what we'll want to do is check for where along that wire path the high current will drop away. And it's at that point that the fault occurs. So if we're turning the controller on and it's giving us these overcurrent errors and it's in short finding mode, then we follow those steps. Otherwise, if it's turning back on and it's not giving us that kind of information, what kind of information is it giving us? Is it saying, all of a sudden zones 18 through 23 are offline? That's a big hint of what's going on. Is it giving us current usage numbers? Is it, what kind of information is it giving us? Let's use that to our advantage. And if it's not an overcurrent problem, we can still use the clamp meter to our advantage to find where that problem is. We can ideally put the controller into short finding mode or wire test mode to give us that source of current rather than the funky waveform that it might be operating on when it's idling. Or again, we can provide our own power supply to supply a current for our clamp meter. Another thing we can do is just take some measurements with resistance from the controller. So we can disconnect the 2-wire path, check the resistance between the 2 wires, and a healthy 2-wire path will have very high resistance between the 2 wires. So above 600 kiloohms or on the CMA 360B, that's pretty much the upper limit of the resistance test on that unit anyway. So it'll probably say OL on a healthy system. There shouldn't be any real continuity happening between the 2 wires. If you even measure between the 2 wires on a decoder, you're really not going to get any continuity there. There's capacitors in there that are keeping things from being one continuous loop. So we want our meter to say either a very high resistance or OL between the 2 wires. Otherwise, we have a problem out there in the field. Also, each wire should have very high resistance to ground. So there shouldn't be anywhere out in the field where the 2 wires are touching the interconductors. The interconductors should also not be touching the dirt out there. And so we can test that, testing resistance between each of these wires and the ground lug in our controller, which is supposed to be grounded. So there'll be a ground wire. This is not a good ground wire. This is just on my test system here, but typically you see a very thick copper wire going to a ground rod or grounding plate, and that's supposed to be installed outside of a certain radius of the controller. But the point being, it's got continuity to the earth coming to this point in our controller. So we can take a resistance measurement between the earth and our 2-wire paths and ensure that it's a high number. Otherwise, it's there's a bad splice out there, or there's a nicked wire, or similar kind of problem. So in order to take a high resistance reading on the CMA 360B, by the way, you will need to take it out of the continuity beep mode, where it's just going to beep at everything under 60 ohms. Will only read up to 650 ohms or so. So to switch it to auto ranging mode, where it has a higher limit, just tap this peak button here, and it'll be able to read up to 600,000 ohms. And then test we can do just to see if the wires are any good. We can short our 2 wires in our 2-wire path at the very far end, and we should now have a very low resistance between the 2 wires. This is just my tiny little test rig, so it's a very, very low amount. But out there in the real world, you'll have longer runs of cable, so you'll see higher numbers. So most common is 14 gauge, which is 2.5 ohms for every 1,000 feet. But obviously, there's 2 wires, so that we have to multiply that by 2, because there's a certain amount of resistance going out and then a certain amount coming back to our other probe. For 12 gauge, it's less resistance, 1.6 for every 1,000 feet, multiplied by 2. If you have a higher number than that, that indicates there's a bad splice and there's corrosion in that splice, or there's something else adding resistance, but typically it'll be a bad splice. Obviously, we can check our solenoids as well using the resistance mode on the meter. You want somewhere from 20 to 60 ohms on solenoids. So overcurrent is when the 2 wires have low resistance to each other or to ground, and this can cause an overdraw current. So if we think back to Ohm's law, there's a amount of resistance that's too low, and with our steady level voltage coming from the controller, the only other variable that can move is, so current's going to increase as resistance decreases. So that's what's causing this overcurrent. This can happen either because the 2 wires are making some kind of direct contact, or they are making indirect contact because they're taking the wet ground and using that as a jumper between the 2 wires. So this can happen either because the wires are actually touching directly, or it could be that there are bad splices and there's moisture getting to the wires, and that moisture is in the surrounding soil acting as a jumper, or it could be that the decoder has failed and it's got its own little shortcut inside that it's now it's burned, and it's allowing current through and causing an overcurrent. So I mentioned ground fault. That can be where, you know, both wires have some kind of contact with the dirt, or it can just be where there's one wire with contact to the dirt and there's current leaking only through that one wire. And in this situation, the controller is not going to give you a whole lot of information about where this problem's happening. It's not going to say, you know, there's a short here and it's only affecting these decoders down here. It's not. It's going to affect everything on this 2-wire path, because the whole thing is just using up a lot of current, and that's all it knows. All it knows is there's a lot of current going out there from the controller. It doesn't know where that high current ends or not. It just knows it's out there, and that's probably the situation where a clamp meter is going to be most helpful, since we have the least amount of information coming from the controller. So, like I mentioned, a lot of controllers will have a short finding or wire test mode, and they'll be able to kind of display how much current is going out there on a particular wire path. And you know, some of the other older or less sophisticated controllers, they might not go into this mode. They might just shut down, and that might be the only clue that you have that there's an overcurrent happening. It might shut down, might blow a fuse. If the controller refuses to with a short in the field, even on short finding mode, one thing we can do is we can splice in a solenoid to one of the 2 wires coming from the controller, and that will add enough resistance to where it can now give you some current from the controller safely. So yeah, adding solenoid to just one of the wires might be good enough to do some short troubleshooting using the controller as our power source, unless it's, you know, permanently damaged, and then you got a bigger problem. So yeah, the solenoid, you know, it's made to operate off of 24 volts of AC, so it's gonna take that AC signal and give you a safe amount of voltage on for the controller. But if the controller can't help you there as far as being a source of current, we can make our own. You'll want to take a transformer that's rated at least for 25 volt amps, or you know, rated for 1 amp of current, and then we'll want to splice a solenoid into one of those 2 wires. The solenoid will limit that current to somewhere around 200 to 300 milliamps, depending on the solenoid and depending on some things, which is, you know, well under the 1 amp limit that we're going for on the transformer. So yeah, if you don't have the solenoid in line, either you're going to burn out this transformer, or you might trip a breaker if it's really high amounts of current. You might even heat up a failed decoder to the point where it melts or ignites or something. So this will be a good idea for a number of reasons here. Here's a few other examples of some of these transformers that can be used as a power source. This one has the transformer built into the plug, and then you have your wires coming off of these terminals. You got your solenoid in line with one of the wires. Here's another example of a 3-prong pigtail going to a transformer, and then somebody put some helpful little clips on the ends of their 2 wires there. So when it comes to checking current with the clamp meter, set it to the milliamps mode there at that first setting, with the rotation of the wheel. Then if you're taking these measurements when there's an idle system and that system is trying to communicate with decoders and those bursts of communication are happening, it'll be helpful to engage the low pass filter, so that you would just hold this button that says hold and it says LPF underneath it. Hold that for 2 seconds. You'll see LPF appear on the screen down here. and it'll help to ignore those bursts of communication. By the way, starting in about 2 months or so, that's going to be engaged by default on our clamp meters. It just sort of makes more sense for irrigation, and the vast majority of people buying clamp meters are people troubleshooting 2-wire systems. So it makes sense to make things a little bit easier for them. And then you will want to clamp around only one of the 2 wires at a time on a 2-wire path. If you have the clamp around both wires, it's basically reading the average amount of current on those 2 wires. And if there's current coming on one wire and going on the other, as voltage sort of flips back and forth, it's going to read that as an average of 0. It's just going to tell you there's 0 current on that cable, which obviously is not true. It's just the effects of the current moving in opposite directions on the 2 wires has a canceling effect. That can be helpful if you're trying to measure the amount of imbalance between the 2 wires. Let's say there's a ground fault on only one wire, it's going to use up more current. So you'll actually see a non-zero number if you're clamped around both wires in that situation. But for the most part, what we want to do is just clamp around one wire at a time when we're taking measurements. So once we do that, once we clamp around, give it 2 or 3 seconds, and you'll start to see a steady number. That number indicates the amount of current flowing out to any downstream decoders. So again, when idle, those decoders are going to consume the consistent amount that they're supposed to be consuming, somewhere between 0.5 milliamp and 5 milliamps. But you're going to want a more specific number to whatever system you're working with. So for instance, Rainbird decoders tend to be between like 0.5 and 0.7 milliamps each. Hunter, depending on when you bought them or what kind it is, there might be somewhere between like 1.5 or 2.5 milliamps each for the ICDs anyway. Other decoders take 5 milliamps, but whatever that number is, it's going to be pretty consistent from decoder to decoder. So we can use that math to our advantage. So for instance, if we have this system with 10 decoders, no matter how much they use each, we know that they're all going to be using the same amount. So they're all using 10% of the total amount of current out on this wire leaving the controller. So here's 100% of the current going out to the decoders. But if you take a measurement here, it's only 50% of what's being used. If you read here, all this current being used by these decoders does not get factored in. So this is kind of the general idea as far as what these measurements are going to mean and when we're doing our math. So one analogy I like to use, again, water is a nice, water always makes for a nice analogy when it comes to electricity. So let's say we're on a cul-de-sac, we're on a street here, and each of these houses is using water from the water main. This part of the street is going to be a lot more water flowing through the water main than this part of the street. There's only 5 houses that this part of the water main is actually giving water to. The reason, some people like to put this in terms of, like the main line going out to different sprinklers and things like that. But there's 2 wires here, so you can think of it in terms of, any water being consumed by this house, it's also going to be coming back through the sewer. So you take a measurement here on the water main or the sewer, the sewer is going to have a lot more water flowing through here at the beginning of the street also. And if you clamp around both wires, how much water is coming and going at the same time, it's gonna average that out to 0. So I like to think of it in terms of kind of water main and sewer line to reflect that there's 2 wires going on. So again, here is where 100% of the water servicing these houses will be flowing, whereas here it's going to be half. So to put this in terms of real world numbers, let's say each of these decoders uses 1 milliamp to make it easy. You're going to see, if you take a clamp meter reading here, you're going to see 5 milliamps. If you take a clamp meter reading here, you're going to see 10. Each of these decoders uses 1 milliamp, 10 decoders. We got 10 milliamps here. So if you have a bad decoder, think of it like a leaky toilet. This house is going to be using a ton of water compared to all the other houses. It's just got running water coming in from the water main at all times, going down straight to the drain. And your reading right here might be normal because all these houses are using what they're supposed to be using. But all of a sudden right here, you've got a high number because there's a lot of water usage happening here. So, here you'll see a high number and know that there's a problem in house somewhere on the street. Here you'll see a high number and you'll know that that problem house is further away down towards the end of the street. Here you'll know that the problem house is further up the street. So that's kind of the idea. We're trying to find, if we're trying to find a bad decoder, we're looking for that where the current goes from high to normal. You can verify that this is our problem decoder by clamping around its wire coming off of the water main or the main 2-wire path, and just see what it's consuming. If you clamp around this decoder wire, it should be 1 milliamp, but here we see it's 209. We know that this is a bad decoder. If we have a short, that means there's water just spewing from the water main straight into the sewer, and it's not even getting water pressure to any of these houses sometimes because the break is so bad. So you'll see huge amounts of readings everywhere along the wire path here. Here you'll see a very low amount or 0, and you'll see all this current activity happening in a high number in this part of the wire path, and a low amount here. A ground fault, again, sometimes it's only one wire that's faulted and giving you high current. So that current is leaking out through the dirt, and the other wire might be giving you normal numbers. So for that reason, you'll always want to check both wires. You might see a normal number on red, not realizing that blue might have its own issue. So again, with our analogy here, think of it in terms of like a fire hydrant that somebody hit and it's spewing water out into the nearby grass. It's not getting to the sewer line, but you're still seeing a ton of water flowing through the water main. So you're going to see high amounts of usage here up until the fire hydrant, but that clue is not there on the red side. So if we have a ground fault, it's usually going to be near a valve box. It's usually going to be a splice issue or a nicked wire from when those wires were stripped. But maybe the wires got nicked when somebody was digging somewhere between valve boxes. So if that's the case, we can find where that's located using our ground fault locator PE 2003. Just make sure that you know the route of the wire path. That'll make it a lot easier. Make sure you isolate both ends of that section of cable. So disconnect from decoders and anything else. You don't want that kind of voltage getting into these decoders or going to your controller. Isolate that section of cable, clip onto both wires here again, because if there's a fault on either wire, this will make sure to pick it up. If it just so happens you do have decoders somewhere connected on this section of cable, in theory, there shouldn't be a big difference in voltage going across that decoder, but again, it's safest to disconnect anything you can. So if we have low current somewhere, that's a problem as well, obviously. If we have a fault here to where these decoders are offline and not using any current, obviously they're not operating correctly. So these decoders could have all been hit by a bolt of lightning and there was grounding here, but this whole section was sacrificed. Or it just could be that there's a bad splice here and these were all disconnected. But either way, it's going to affect your numbers when you're taking measurements. And if it is that they're disconnected, we might call this an open. There's an open in the line. So what that might look like in this house analogy, if there's somebody shut off a valve here and these 3 houses don't get water service all of a sudden, it's affecting your amount of water usage upstream as well. And then, nothing happening down here in the water main. So in kind of a more real world situation, when we're kind of doing the math and comparing these numbers, it's best to look at your system when it's healthy and record the baseline usage. We can kind of do the math ourselves and say, we have 28 decoders and they should each be using 1.4 milliamps, but it's better just to take a baseline reading of a healthy system and know when that changes. But let's say we don't have that baseline number, we can do this math. We can say 28 decoders, 1.4 milliamps each, we should have roughly 39.2 milliamps consumed on this entire wire path, coming out of the controller, and take a measurement there. So when we take readings, it's the amount of decoders downstream times the current draw of each of those decoders. So yeah, here we're halfway. We want 19.6 milliamps on our clamp meter when we're clamped around on wire. If we have a higher number than that, if we take a higher number here at the beginning, we know that the problem somewhere on this wire path is a short or a ground fault, and there's extra current being used. If it's lower, then we have an open somewhere. We have a break somewhere, or we have offline decoders. So take measurements at different points and just kind of compare it to what you're expecting to tell you what kind of problem and where it is. So in terms of kind of narrowing down where problems are, if we have high current coming from the controller onto a ground, a wire path, then we're going to look for where that high number drops away. So that number, if we take another measurement, let's say here, we know that our problem is still downstream. If we take a measurement here and it's a lower number, we know our problem is upstream. So just keep that in mind. If you have a high number, the problem is downstream. If your problem is not high or it's low, your problem is upstream. So as we narrow things down closer and closer, we'll be able to locate exactly where our problem is. So what's the most efficient way to do that? We kind of break things up into halves, right? So we start here at the beginning of the wire path. We take a measurement. Yep, we have a high number. Let's go halfway down the wire path and take a measurement. So we go halfway. We have a high number still, so we know we need to advance further to the right. So now we have a normal or a low number. We know we've passed where the change occurred. We go back halfway to our last previous measurement. And now we have the problem narrowed down between these 2 points where we measured high number, low number. The problem is in this valve box right here. So not every wire path is just a straight line, obviously. So you're going to want to take strategic measurements. So whenever a wire path branches off, take a measurement at the beginning of each branch and just see if it's the number that you expect there. And some things to consider: splices and wires damaged during stripping are typically where the problem will occur. So that's kind of what we're looking out for. Even if it's a bad decoder, that's an indication that there's probably another problem. But that's another thing we want to isolate. Is this high current coming from a decoder? And then last, is it a wire break somewhere? And then in terms of an open versus a ground fault, sometimes the difference between an open and a ground fault really is just how wet is the dirt in the valve box. How much conductivity is there happening due to moisture in there? You might have an overcurrent right after it rains. Meanwhile, you have decoders offline when it's in drier weather, and that's just because there's a wire exposed and it's making electrical contact when there's water, and it's just adding resistance when there's not. So when there's a short or a ground fault, there's some kind of high current going on. Your controller is not always going to be so helpful in giving you clues as to where that is. So a clamp meter is going to be most helpful in those situations. So kind of a quick reference on what we're doing with these measurements. If you have high current at the controller, that indicates that there's a short or a ground fault out there somewhere in the wire path, or a bad decoder. So advance halfway down the wire path. See if you still have a high current. If so, your problem is still further downstream. Go halfway. If not, your problem is further upstream. Go halfway that way. And as soon as you find where there's the change in the current, you found where the fault is located. If the amount of current coming out of the controller is less than it should be, you've got a disconnect happening somewhere, or a bad section of decoders. See what the controller tells you as far as which decoders are offline, and that will be a big hint. Find out where that current drops off and goes to zero, and then you found where the fault is. So just to go through an example of kind of start to finish, let's say we have a system with 10 decoders, and each one uses 2.5 milliamps. Here we can see total of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decoders on this wire path here. So the expected total current that we should see at the beginning is 10 times 2.5 for 25 milliamps. So let's take a measurement and see what we actually read. And here we go. We have 80 milliamps. We have a problem out there. So what do we do next? That indicates that the problem is downstream. Obviously, we're upstream of everything. So you would think go downstream, but this is kind of a trick question. We have to make sure we measure both wires before we make any conclusions. So measure red and blue in case there was a ground fault on just the red wire. But here we have 80 milliamps on both wires. So that indicates we have a short. We have high current on both wires. That's a short. So from here, we'll go halfway down the wire path to where there's equal numbers of decoders upstream and downstream. So where is that? It's about right there. We have 5 decoders downstream here, and we're seeing a normal number, 5 times 2.5. So let's go upstream. Let's measure either these 2 decoders or these 2 decoders and see what we find. So let's go here. We got a normal number, no problem. So let's go to the other leg here. We don't have to move too far, luckily. And here we see a high number. So we know our problem is somewhere on this leg. So it's either the first valve box there or the second one. We might as well just go to the nearest one and make it easy on ourselves. So let's check what's going on in this valve box here. We see a high number. We know that this is where the problem is. We can verify that it's this decoder because this wire is just coming from the 2-wire path to this decoder. This is what's using all our current right here. So let's replace this decoder and reconnect to the wire path and see if we're all good. And we can also just take that decoder, plug it into the controller, see if it gives us errors there, and we can verify that it was the decoder that was the issue. If this had just been a bad splice, this would have been kind of a normal number over here, and all the high current would have been traveling through the dirt between these 2 wires at these bad splices. But we measured this actual decoder wire and verified that it contained the problem. And then just to talk a little bit about, what would we have done without a clamp meter in this situation? We would have had to, instead of go halfway and clamp around the wires, we would have to break half of the system off from the controller and see if that clears any errors on the controller there. Or we would have to take a measurement with a multimeter and see if we're getting the correct amount of voltage here, check and see if the resistance on this end is high like it should be, check if resistance over here is high. We'd have to take various other steps where we break the system in half and then break that system in half and keep breaking connections and walking back and forth from the controller and checking for errors. And, so obviously the clamp meter is a big time saver and a big saver of splices. So with that, we're at a little over an hour, so sorry to take up a lot of time, but let's see if there's any questions at this point.
I have one, Alejandro. What does it mean if there's an overcurrent error only when a zone is operating?
So let me back up and just kind of use this as an example. So if everything's normal, but let's say this zone is operating and then we have a high current, that means the short is on the other side of the decoder, and it's either a shorted solenoid or the splices on the other side of the decoder are bad, and so those are causing a short when the zone is trying to operate. Otherwise, if this system is idle and that's not happening, this solenoid or this valve doesn't come into play. So if that's only happening when this zone is active, that means it's on the other side of the decoder, not on the 2-wire path side, but on the valve side.
Thank you. We just got another question. Would you explain LPF low pass filter?
Yeah, low pass filter. So that ignores frequencies. So this clamp meter is always measuring alternating current, and that's electricity wiggling back and forth on these wires, and the frequency with which that happens on the plug coming out of your wall is 60 hertz. So some systems will use 60 hertz. Some of them will use very low frequencies, like I said, like 1.2 hertz and things like that. But sometimes the communication happens at higher frequencies. The low pass filter on the CMA360B means it's trying to ignore everything above 160 hertz, everything happening faster than 160 times a second. So all those little communication signals, they're very quick little bursts of data happening. So the low pass filter is going to ignore those, but it's the main current going out into the system is going to be unaffected. The idle current of the system will be unaffected.
If you have any questions, please contact us in the meantime, and have a good rest of your day.
Thanks everybody for being here. Appreciate it.